You and I, along with everyone else alive today, is related to each other through one man and one woman. We know this thanks to two special pieces of DNA which we'll be covering in today's video. We can say this because DNA keeps a record of ancestry. You get your DNA from your parents, who got their DNA from their parents, and so on, their ancestry. As DNA gets passed on down the generations, it gets diluted. You have half of your parent DNA, you have a quarter of your grandparents' DNA, and going back 7 generations, each of your great-great-great-great-great-grandparents will have contributed on average less than 1% of their DNA. Now there are 2 exceptions to this rule: mitochondrial DNA, which is inherited through the female-only ancestry of a person, and the Y chromosome, which is inherited through the male-only ancestry of a person. Now the reason why these 2 pieces of DNA are the exception to the rule is because they're inherited differently to the rest of your DNA. A mother will pass on her mitochondrial DNA to all her children, but the father won't. As we go through the generations, it means that only the female line is passing on the mitochondrial DNA. This means that mitochondrial DNA can be used to trace the female-only ancestry of a person. Now the Y chromosome is a little bit different. While everyone has mitochondrial DNA, not everyone has the Y chromosome. This is because the presence or absence of the Y chromosome determines whether or not a person is male or female. A male with the Y chromosome will pass on the Y chromosome to his male offspring. And likewise, as you go through the generations, only the males will have the Y chromosome, meaning that the Y chromosome can be used to trace the male-only ancestry of a person. If you're lost at any point in the video, feel free to rewind and watch again. If you're still having trouble, leave a comment below and I'll get back to you. This female and male-only lineage is important because when we compare it from a set group of people, we're able to see the family relationship between those individuals. If, for example, we use mitochondrial DNA to look at the female-only ancestry of a population of people, we would compare the mitochondrial DNA from each of the members of the population. The more similar a sequence is between 2 members of the population, the more closely related those people are said to be. The more dissimilar the sequence, the more distantly related those people are said to be. When we do this for each of the members of the population, you're able to build a family tree showing the female-only ancestry of that entire population. So using this concept in mitochondrial DNA from people all over the world, we've been able to show that yes, we are in fact all related to each other. We all descend from one woman, our most recent common female ancestor, imaginatively nicknamed Mitochondrial Eve after the biblical mother of all humanity. And likewise, the same thing has been done with the Y chromosome. Using Y chromosomes from males all over the world, we've been able to show that all males alive today descend from one man, the most recent common male ancestor, nicknamed Y chromosome Adam. Now it is worth noting here that just because we all descend from one man and one woman doesn't mean that they were the first man or woman that we all descended from. For example, say if all the males in a population died out, except for one family, then the head of that family will be the new Y chromosome Adam. So now that we have this family tree and we can see the relationship between everyone, we can then ask the question of, when did these 2 people live? The method we use to determine this is what's called a molecular clock, in which we work out the mutation rate, that is the rate at which mutations occur for mitochondrial DNA and the Y chromosome, and then using that mutation rate we then scale that to infer how long ago these common ancestors of all humanity lived. There's usually 2 approaches for when this is done. One is to take large-scale structures of the family tree. This is typically done by comparing humans and chimpanzees, which using the evolutionary model is assumed to have a shared ancestry about 6 million years ago. When doing this, the shared human ancestry comes out about 200,000 years ago, which according to the evolutionary model is about the rise of modern humans. Now, the other method is called the Pedigree Method. The sequence, whether it be mitochondrial DNA or the Y chromosome, of both the parent and the child, and then goes, okay, well, this many mutations occurred over 1 generation, and we see 1,000 times that, then we know that there have been 1,000 generations. But you divide that by 2 because you start with a single point and you have 2 different mutations, so that's 500 generations. Anyway, as we scale that mutation rate up across the full diversity that we see across humans, we find that the human female ancestor lived about 6,000 years ago and the human male ancestor lived about 4,000 to 5,000 years ago. Wait, that's a big difference between 200,000 and 6,000. This discrepancy is known. It's largely discarded because it doesn't fit the model. Now, what's the solution here? Some early suggestions included maybe the mutation rate was slower in the past and now it's quicker in the future. And by having our quick mutations in the present and assuming the same rate, then it gives us the appearance of having a recent shared ancestry when we really had an old one. But as for how that works, we don't really have an answer. Another suggestion put forth, there's a mutation but then it mutates back. But in doing so, that needs to happen like 40 times. Because if it's mutating there and back again, it doesn't give much credibility for the family relationship that we talked about in the family tree earlier. So another suggestion put forth is, what if you have the family tree spread out, but the more extreme branches of the family tree where there are greater differences get cut off, leading to fewer differences. If that's the case, then we've got a shared ancestry of only a few thousand years ago. Another suggestion that's been put forth to explain this discrepancy is to say that the high mutation rates in the present aren't really mutations that are passed on from generation to generation. The reason that they give that, they say that the mutations in the parents aren't given to the children. The mutation rate is and always will be the same slow mutation rate that gives us a shared ancestry of 200,000 years ago. But when you look at the raw information from the paper that they're inferring, it tells a different story. While yes, there are mutations that aren't passed on to the next generation, there's still mutations that do make it through, and at a rate that suggests a shared ancestry of only a few thousand years ago, rather than a few 100,000 years ago. This is interesting because this is exactly what we would expect based off the biblical account in which God supernaturally created one man and one woman about 6,000 years ago. Now, for the Y chromosome, we know that all males except for Noah were killed off as all the world was wiped clean in the flood, in which only Noah, his wife, their 3 sons and their wives were the 8 people who regenerated the human population on Earth. Now, if this is the case, then we would expect to find the Y chromosome family reach back to a single male ancestor about the time of the flood. Now, dating with the Y chromosome gets tricky. 1, because it's so much larger than mitochondrial DNA. 2, because parts of the Y chromosome are shared between the Y chromosome and the X chromosome, meaning that there's some crossover going on there, which means we can't use that for dating the Y chromosome. 3, there's repetitive bits that are hard to sequence using our modern method, so we ignore these areas too. When we compare the Y chromosome mutation rate from father to son in the areas that aren't affected by those issues that I talked about, we find that the mutation rate suggests a recent origin for the Y chromosome, somewhere in the order of 4,000 to 5,000 years ago. Now, although the Y chromosome family tree mutation rate suggests that the shared male ancestor lived before Noah, this can be accounted for by the fact that the father-son mutation rate in the Y chromosome has only ever been measured in Europeans, whereas the most distant branches that exceed this is within a subset of the African population. By assuming a slightly faster mutation rate in some branches of the African tree, this brings the shared male ancestry back to the time of Noah. With all of the support for the old age of human ancestry having fallen short, we're now left with evidence that supports with a biblical account of creation in which God supernaturally created one man and one woman about 6,000 years ago. But for now we can know that we all share a recent ancestry through one man and one woman, and we know this thanks to the mitochondrial DNA and the Y chromosome. And by comparing these 2 pieces of DNA from people all over the world, we can see the relationships between different members of the human population. Furthermore, by looking at these sequences between parents and children, we find that the mutation rate suggests a recent human origin for both the male shared ancestor and the female shared ancestor. This is exactly what we'd expect to find based off the biblical account. Now for those that are a bit uneasy about having slightly different mutation rates for different parts of the family tree, there's a great publication which I'll talk about in the next video which links the branches of the family tree to the human population size. In doing so, we find really strong evidence for a recent, not old, human ancestry. So check that out, and until then, God bless.